Hello everybody. This first lecture of my course will be on three-dimensional laser imaging, and I would like to start with by citing Emile Zola, who will say that, in my opinion, you can't say you have thoroughly seen something until you have a photograph of it. This actually very well describes what we want to do with different types of imaging, such as confocal microscopy, multi-photon microscopy, and different other nonlinear microscopy techniques. What we really want is to see the sample better and resolve all tiny features in the sample. So my name is Smalyukh. I'm from University of Colorado at Boulder. This is our web page and my contact information, and I would like to give this outline of my lecture today. So I'll talk about different types of imaging techniques, and in particular confocal microscopy and multi-photon microscopy. In both of those imaging approaches, we use tightly focused laser beams, and this allows us to achieve several different goals. So first of all, having tightly focused laser beams allows us to have more energy per unit area in the sample. Second, this allows us to limit the area of illumination in the sample, and you will see how this is important to obtain resolution in 3 dimensions. So in addition to confocal and multi-photon microscopy approaches, during the ICAM summer school, you will also learn about other 3-dimensional optical imaging techniques, including coherent anti-Stokes Raman scattering microscopy, second and third harmonic generation, multi-modality imaging techniques, and so those will be those lectures will be given later on during the summer school. But let me briefly remind you about a very important parameter of any optical imaging system called numerical aperture. So numerical aperture is defined as a product of the refractive index of the coupling medium between the objective and the sample, such as immersion oil or air, multiplied by the sine of the theta, angle theta, which is the half angle of the cone of light collection in here, light collection cone. And so you will see that numerical aperture is a very important parameter which will determine the resolution of the optical imaging system. It also determines what kind of depth of field we have, and so you can see from this cartoon here that the higher is the numerical aperture, the smaller is the depth of field, and vice versa. And this image over here shows axial intensity distributions for different planes with respect to the focal plane of the given objective. And so as we would go upward or downward with respect to this focal plane, the axial intensity distribution would have appearances shown on those figures. The other important thing to remind is the point spread function, which tells us, which describes the response of an imaging system to a point source of light or object that we study, and this is the general form usually used to describe point spread function, also plotted in here, and we will learn more about point spread function, including unconventional ones, again later on during the summer school. However, what is important is that the point spread function of the imaging system determines the resolution of this imaging system. And in order to determine the resolution, we often use the so-called Rayleigh criterion, which tells us when when the center-to-center distance between the two peaks over here is less than the width of those peaks, the two peaks are assumed to be indistinguishable with respect to each other, and therefore they can be resolved. And vice versa, if this distance between the centers of peaks is larger than the width of those peaks, then we can resolve them, as shown here in this illustration. And so now we will proceed to the basics of confocal microscopy. This slide over here shows the principle of confocal microscopy as it was originally proposed by Minsky several decades ago. So the basic idea is that one uses one pinhole to illuminate a certain point in the sample, tiny volume in the sample, and then the other pinhole, both of those pinholes being in the planes confocal with the point of study in the sample, with the volume of interest in the sample, and then the second pinhole is used to block all unwanted light, so that only light from this volume of interest would be able to go to the detector, such as photomultiplying tube. And so this very simple idea allows you to achieve three-dimensional resolution, because now you can obtain information from a given volume of interest in the sample, and you can resolve features not only in the plane of the sample orthogonal to the optical axis of this imaging system, but also along this optical axis. The reason for this new capability is very simple, because all light coming from outside of this focal point, which is confocal with the two pinholes, two apertures in here, all light outside of this volume of interest will be not efficiently focused into this pinhole, and therefore will be effectively blocked. So then the sample is scanned point by point, as demonstrated in here, and the information on the intensity data is stored in computer. Later on, this information is used to reconstruct a three-dimensional image. So since the time when Minsky first proposed the confocal microscope that we just discussed, there have been many developments in the confocal imaging techniques, and in particular it's useful to use fluorescent dyes in order to enhance contrast in this imaging technique, and therefore improve the imaging capabilities. So usually we use fluorescent dyes that have certain absorption spectrum and emission spectrum, and those two spectra are separated. The peaks, the maxima of absorption and fluorescence, are separated from each other. The difference between the wavelengths of absorption and fluorescence is called Stokes shift, as you know. And so, because of this spectral separation of absorption and fluorescence, one can excite the fluorescent dye using particular laser lines, such as argon laser at 488 nanometers, as shown in here, and then the fluorescent light can be detected at a larger wavelength, at a longer wavelength, as shown in here, by blocking all the excitation light that might be still coming to the detection system due to reflections and other reasons, using the interference filters. And so in here, we illustrate the spectral range of detection of the fluorescent light in the case of this particular fluorescent dye. So, typical examples, you can see in here, for example, the dye for which we excite. We use argon laser for excitation at 488 nanometers, and then fluorescence light is detected in the spectral range of 510 to 550 nanometers. So this imaging technique has been, confocal imaging technique, has been widely used in biological and material sciences. And in here you can see a modern version, a schematic representation of a modern fluorescence confocal microscope, in which instead of the regular light source like in the original approach proposed by Minsky, one uses excitation beam in the form of laser light. Therefore, you do not need to use one of those pinholes for excitation. Instead, you simply use a laser light source for excitation. And so this laser light is going through a beam splitter and then tightly focused into a tiny volume in the sample using an objective lens as shown in here. The fluorescent dye molecules in the sample are excited mostly in the vicinity of the focal plane in this focal region. However, the dye molecules outside of this focal region of interest can be somewhat excited too. So then, in the epifluorescence mode fluorescence confocal microscope that's depicted in here, the fluorescent light is detected in the backward geometry using the very same objective lens shown in here. And then, because this beam splitter is designed in such a way that it reflects the longer wavelengths of the fluorescent dye, so of fluorescent light coming from the sample, the fluorescent light will be reflected in this direction, and then there is another lens which allows you to focus this fluorescent light through the pinhole, and then the light is detected using a detector such as photomultiplying tube. And so just like in the previous case of the scheme proposed by Minsky, all light that's coming from outside of the focal plane, this focal region, is effectively blocked by this pinhole because it's not effectively focused through the pinhole, and therefore only a small fraction of it can reach photomultiplying tube. So this way we can again achieve three-dimensional resolution. And in here you can see the typical both radial and axial resolution of the confocal microscope. Of course, it depends on the wavelength of light used for imaging, and the typical resolution that can be achieved for radial directions is of the order of a quarter of micron. The axial resolution is usually somewhat worse, and it can be as good as half micron, provided that we use high numerical aperture objective. So what's important to notice in here is that the radial distribution is, the radial resolution is inversely proportional to so the radial resolution is inversely proportional to numerical aperture, whereas axial resolution is inversely proportional to numerical aperture squared. And so this means in confocal imaging we really want to use high numerical aperture objectives because this allows one to achieve much better resolution, especially in the axial direction, which is very desirable from the point of view of getting insights about the structure of the sample. So what you can see in here in this image that I showed is a fluorescence confocal microscopy image of biological sample in which different colors represent, give you information about structure of this sample. So using this technique in biology and also in material science, one can learn about chemical composition and structural properties of different composite materials or biological systems which have very different types of molecules and different soft materials systems with different components. Later on during this lecture we'll also discuss somewhat different type of confocal imaging which is used for visualization of patterns of molecular orientation in soft matter systems such as liquid crystals. And so in this case it's useful to modify such a confocal microscope with a device that allows you to control polarization state of excitation and detected fluorescence light at the same time. And this can be achieved, for example, using a twisted pneumatic polarization rotator or ferroelectric liquid crystal polarization rotator. This device will simply allow you to not only control polarization of excitation light, but also the polarization of detected light, and therefore one can obtain information about not only spatial distributions of different chemical components in the sample, but also about patterns of molecular orientation, such as those of liquid crystal molecules in materials similar to pneumatic liquid crystal fluids shown in here. So the basic features of this approach are then that one uses polarized excitation and fluorescence detection, and in addition one also uses fluorescent dye molecules that align and follow orientation of those liquid crystal molecules in this particular case, and this allows for visualization of patterns of molecular orientation. It is possible not only to use one fluorescent dye, but multiple different fluorescent dyes can be used for labeling either biological or materials systems. And so in here I just give you several examples of dyes that can be used. You can see that the particular dyes I show it here have fluorescent bands of both absorption and fluorescence bands quite far from each other in the spectrum, within the spectrum, visible spectrum of light. And so you can see that ion dye shown in here has the absorption band somewhere between 450 and 500 nanometers, emission band between 500 and 550. The nile red dye, however, has absorption band at much larger wavelengths, and respectively the emission band at even longer wavelengths. So what this allows us to do is to use now two different lasers to excite those dye molecules separately in the sample, and detect fluorescence light from those dye molecules separately, and therefore visualize material composition of samples where different dye molecules can label different components within the sample, or biological tissue where again different dyes could label different biological molecules, for example. And so the two-channel fluorescence confocal microscope is depicted on this slide. You can see that the general principal scheme of this microscope remains pretty much unchanged. The only change is in the detection part of this system, and so now we can use not only one but two different laser beams in order to excite the sample. The fluorescent dye, the fluorescent signal from both of the dyes would go in the backward geometry, just like in the previous case that we discussed already, and will be focused through the same pinhole. However, because the absorption and because the fluorescence due to two different dye molecules is at within different spectral ranges, as you can see here, that means we will be able to use another beam splitter and separate the fluorescent signal coming from the two different dyes. Therefore, those two fluorescent signals can be separately detected using two different photomultiplying tubes. And therefore, we can detect separately fluorescence signals, fluorescence textures from different dyes separately, and then colocalize the images, this way obtaining information on structural composition of the samples in 3 dimensions. The examples of biological imaging are illustrated on this slide, and you can see that not only we can use two different dyes, so the colors actually correspond to different dyes in the sample, and you can see we can use not only two different dyes to label different components in the sample, but also multiple different dyes, for example 3 or even more. Everything depends on how narrow, how many different dye molecules you have in the sample, and of course if you want to do labeling of the sample with multiple dye molecules, it's important to have relatively narrow absorption and fluorescence bands so that there would be no significant overlap, and those studies could be carried effectively. What I want to show on this slide is a typical a picture showing you a typical fluorescence confocal microscope. In this particular case, this is Olympus Fluorview 300 fluorescence confocal microscope with 5 different laser lines, so potentially one can use this system for imaging of 5 different dye of the sample labeled with 5 different types of dye molecules, and the fluorescence confocal scanning unit is shown in here. So those are the spectral, the 5 different laser lines that I mentioned in this particular system. One disadvantage of fluorescence confocal microscopy is that the imaging is relatively slow. We understand that in order to obtain an image like this, we need to scan the excitation laser beam point by point throughout the sample and detect fluorescence light from each of those points. And of course it takes time because, first of all, the scanning is relatively slow. It's usually done using galvo mirrors. The second problem is that you can't have very short you can't detect the fluorescence light within a very short period of time from each of those points in the sample, because you need some time to integrate the signal to accumulate the fluorescent signal in order to have it relatively strong and therefore the images of good quality. And so this means that to obtain a good image of this quality, it usually takes you seconds, or in the case if you obtain a three-dimensional image, it can take minutes and even more. So this drawback of the confocal microscopy, as you understand, would not allow you to do dynamic imaging of different dynamic processes in both biological and material systems. However, recently the new confocal imaging approaches have been developed, and one of the fast fluorescence confocal imaging approaches is depicted in here. This approach is based on the so-called nickel disc that you can see in here, which is mechanically coupled to a disc with the coaxial system of lenses, and this disc is being spun, rotated. So the idea of this imaging system is as follows. We again can use laser or other monochromatic source of light for excitation, and then the excitation light is going all the way through the disc with micro lenses and also the pinholes, all the way to the sample through, for example, twisted pneumatic polarization rotator in the case if we need to control polarization of light, and then it's focused into the sample. Just like in the case of the regular confocal microscopy approach, the fluorescent light is propagated in the backward geometry through the same system of pinholes in the spinning, rotating disc, nickel disc, and then because of this beam splitter in here, the fluorescence light at a longer wavelength is not able to go through it, but is reflected in this direction, and then reaches the photodetector such as a camera. Now, unlike in the case of regular confocal microscopy, in this approach it's possible to illuminate the sample, entire sample at once, not point by point, and the reason is because we have not just one, but many of those pinholes. And because the speed of light is very high, that means that the excitation light and the detected fluorescence light are essentially passing through the same pinhole, which did not rotate too much during the process of excitation of the dye molecules in the sample and light propagation between the pinhole and the sample. And so this means that we preserve the confocal imaging principle, and this allows us to image the sample with three-dimensional confocal microscopy resolution, however, much faster because the entire sample can be illuminated through multiple pinholes in the rotating nickel disc, and therefore, instead of scanning point by point, we can achieve the image of the sample in the given confocal plane at once, which highly increases the speed of confocal imaging, and the speed of imaging can be 1,000 or even 10,000 higher than using the conventional confocal microscopy approach. So the speeds that could be achieved in principle are reaching the orders of 1,000 frames per second, in order to do this, one has to use cooled EM-CCD camera detectors, and the reason is because one needs pretty good resolution, one needs pretty good sensitivity, since the fluorescent signals are relatively weak. As I mentioned it before, the other approach that also allows for three-dimensional optical resolution in imaging in 3D is the multi-photon excitation microscopy, and in particular the two-photon fluorescence microscopy. In this process, one uses the energy from two or more photons in order to excite each dye molecule. And the Jablonski diagram for this case is shown in here. As you can see, that the two photons have to be absorbed at the same time. Then there is non-radiative process, just like in fluorescence, in the fluorescence case, regular fluorescence case, and then the fluorescence process at the wavelength which is, however, now shorter than the wavelengths of excitation, because two photons have been used to excite the dye molecule. And so so the intensity of the exciting light falls very fast above and below the focus, and this allows you to achieve the three-dimensional resolution without actually using pinhole that was absolutely necessary in the case of conventional confocal microscopy. The reason is because this very sharp decrease of the excitation and the fluorescence light as one would move away from the focal point allows you to effectively excite and detect fluorescence light only from the very vicinity of the focal point of the particular imaging system. And so in the case of the two-photon fluorescence microscopy, the emitted fluorescent light is proportional to excitation intensity squared. However, this means that in order to achieve strong fluorescent signal, one needs relatively high laser excitation intensity, and this is the reason why in two-photon fluorescence or other multi-photon fluorescence approaches, one usually uses the pulse lasers that allow us to achieve high instantaneous intensities at moderate average powers delivered to the samples. And so here I give you one example of the typical laser powers that could be used in the two-photon fluorescence microscopy approach. So if one has average laser power, it's a specimen of the order of 100 milliwatts focused into the diffraction limited spot, which is of the order of 0.5 micrometer in diameter. That means the average laser power in the spot is of the order of 5 by 10 to the power 7 watt per centimeter squared. And because this laser is on for 100 femtoseconds, therefore the pulse duration to gap duration ratio is of the order of 10 to the power minus 5, and this gives us instantaneous laser power when the laser is on of the order of 10 to the power 12 watt per centimeter square. So this means we have very high instantaneous laser powers, as depicted in here, and the two-photon fluorescence process can be very effective. The advantage of two-photon fluorescence microscopy and other nonlinear microscopy techniques that you will learn about later is that usually one can excite the dye molecules using this two-photon fluorescence process by using laser beams at within the near-infrared spectral range, and you can see from this graph showing in here the biological transparency window. You can see that this near-infrared spectral range is very useful for this excitation process, because the biological specimen do not absorb or scatter light within the spectral range, and this means that the excitation light can penetrate deep into the biological samples. The picture in here shows a typical fluorescence, two-photon fluorescence microscopy, and the setup, as you can see, it's very similar and can be built around the same microscope as in the case of confocal microscopy. So, unlike in the case of confocal microscopy, however, one can achieve much deeper imaging of the samples using this approach, because there are not so many losses due to scattering and absorption when this excitation is done within the near-infrared spectrum of the spectral range. And so in here you can see an example showing that it's even possible to image the samples as deep as of the order of 1 millimeter. So to summarize, there are certain advantages and disadvantages from the point of view of the two-photon fluorescence or multi-photon fluorescence microscopy as compared to the confocal microscopy. And so, as I mentioned before, one important advantage is that we have the ability to work with thick samples, because the scattering and absorption losses of excitation light are much smaller. The other advantage is that we do not need the pinhole in the case of two-photon fluorescence microscopy, since light is coming mostly from the focal point in the sample anyway. And it's also possible to excite UV and visible dyes by using visible or near-infrared laser beams through the 3-photon or 2-photon fluorescence processes. The same things, the same reasons, due to the same reasons, we also have lower photo damage and lower out-of-focus photo bleaching, which is again a big advantage from the point of view of biological and imaging and material science. The advantages, disadvantages, however, are also quite serious. So, first of all, the two-photon fluorescence and multi-photon fluorescence imaging approaches usually require expensive lasers, so they are not as affordable. The multi-wavelength imaging is a lot more difficult, unlike using the fluorescence confocal microscopy, Again, in the case if we need to visualize many different components in a heterogeneous system, the confocal microscopy approach would turn out being useful. So within the second part of the lecture, I would like to show you more detailed examples of application of the confocal microscopy technique to image molecular orientation patterns in liquid crystal materials. And in here you can see a very oversimplified representation of the liquid crystal state of matter, which stands in between the solid crystals, which have both positional and orientational ordering, and isotropic fluids, which can flow and have no ordering at all. So liquid crystals are media which combine those properties of solid crystals and isotropic fluids in a very unusual way, because they can have some degrees of order, such as orientational order in the case of nematic liquid crystal depicted in here, and at the same time they can also flow just like isotropic fluids. And so because of this, they are of great interest for many applications, and you all know about liquid crystal displays, of course, but in both fundamental science and also in applications, it's very important to be able to visualize the patterns of molecular orientation in those systems with long-range orientational ordering. And so the average molecular orientation, and the molecules can be of the order of 1 nanometer in those systems, but average molecular orientation is usually described using the liquid crystal director, as depicted in here, using this double arrow. Again, I would like to proceed by starting with the citation of those words by Nobel laureate Lejeune, who said that the study of liquid crystals is complicated because it involves several different scientific disciplines and also a certain sense of vision in three-dimensional space in order to visualize complex molecular arrangements. So this is exactly what we want to use the confocal microscopy imaging techniques to visualize those patterns of molecular orientation, so that some insights into the structures of orientational order in those systems can be obtained from experiments using fluorescence confocal microscopy technique. But before we proceed with that, I would like to mention the other different imaging approaches that are widely used for imaging of molecular orientation patterns in liquid crystals. And the classic approach is the polarizing microscopy. You can see in here a typical texture of liquid crystal, where we have a certain pattern of molecular orientation, in the imaging technique of polarizing microscopy, one usually sandwiches the liquid crystal sample in, for example, liquid crystal cell, between the crossed analyzer and polarizer, and then the sample is observed using an optical microscope in transmission mode, for example, or in reflection mode, as depicted in here. So if we have the polarizer and analyzer crossed with respect to each other, and liquid crystal is liquid crystal sample, such as nematic liquid crystal, is nothing else but an optical crystal with certain orientation of optical axis parallel to the liquid crystal director that can change in space within the sample. So our goal now is to be able to visualize the patterns of molecular orientation in 3D in this liquid crystal sample. And so the intensity of transmitted light that would pass through this system of liquid crystal between the cross polarizers can be described using this equation in here. So this intensity in polarizer microscopy representing a texture similar to the one I shown here as a function of coordinates. So this intensity will be, of course, proportional to the intensity of the light source, and then sine square of 2 beta, where beta is the angle that the optical axis or liquid crystal director makes with respect to the polarizer orientation, and then sine multiplied by sine square of half of phase retardation within the sample as light propagates from one polarizer from the polarizer to the analyzer. And so the problem is that we usually, if we have a three-dimensional distribution of liquid crystal director, a three-dimensional structure in here, what we obtain is an image like this, and each intensity point in this image is an integral giving us some information about what's happening within the sample across its thickness. However, we are not able to resolve the details of this molecular rotation pattern across the thickness of the sample. And so, therefore, since we have only two-dimensional image of the three-dimensional directed field, we will have to essentially guess the how the intensity of light in all of those pixels of the image are related to the maybe very complicated distribution of liquid crystal director across the sample thickness. And this is possible in many cases, but such imaging is not very direct and of course requires very thorough analysis of such a system. Now, in the polarizer microscopy, as you can easily realize by looking at this equation in here, we have the image, the intensity is low minimum whenever optical axis is parallel to the polarizer, and also when it's orthogonal to the analyzer for the planar sample in this particular case, and the intensity is high when we have some angles in between. The reason, of course, is because we have sine squared 2 beta in this equation. And so that means if we obtain a texture similar to the one shown in here, where the optical axis actually changes as a function of coordinates, it's not very easy to find out whether the dark brushes in such a texture corresponds to orientation of the polarizer of the optical axis parallel to analyzer or parallel to polarizer, because both of those cases will give you the dark, the low intensity and therefore dark brushes. Likewise, it's not also possible to distinguish the different mutually orthogonal optical axis orientations at the intermediate angles. And so, for example, if you have a polarizing microscopy texture with many different defects, such as those shown in here, it's not possible to find out what is the sign of the strength of those defect lines based on a single image of this kind. One would need to either rotate the sample and see how the dark brushes in such a texture are rotating with respect to the rotation of the sample. Either they are rotating in the same direction or in the opposite direction, and then this would give either positive or negative signs for these types of particular disclinations. On the other hand, one could also use additional phase retardation plates and other means to distinguish those defect lines which from an image like this look quite similar to each other. However, the fluorescence confocal microscopy in polarizing mode, as you will see in just a little bit, will allow us not only to visualize the patterns of molecular orientation in 3 dimensions. You will see that it's also possible to more directly image the pattern of molecular orientation because the principle because of the principle of this fluorescence confocal polarizing microscopy, where the intensity of light is very directly related to orientation of the dye molecules and liquid crystal molecules with respect to the excitation and detection polarization direction. So I again show you this slide which I already showed before. This is the fluorescence confocal microscopy principle scheme, in which the 2 major features that distinguish it from conventional confocal microscopy imaging are polarized excitation and fluorescence detection, achieved in this particular case using polarization rotator, and also the fluorescence dye alignment, and this is achieved by using special dye molecules with the transition dipoles of absorption and fluorescence parallel to the long axis of the molecule, so that whenever we have so that the fluorescence intensity patterns can be used to visualize molecular orientation distributions in liquid crystals. So in here you can see a typical dye molecule BTPP that's used for such applications. And so as I mentioned before, this dye molecule has transition dipole moment of both absorption and fluorescence parallel to the long axis of the molecule. Moreover, you can also see that this molecule has a rod-like structure. That means it's similar to the shape of liquid crystal molecules, and therefore such molecules dispersed in liquid crystal are following orientation of the liquid crystal molecules as depicted on this image here. So another important thing is that both absorption and fluorescence band are polarization dependent, and because of this orientation of the transition dipole moments of the dye molecule along the molecular axis, and the dye molecules following orientation of the liquid crystal molecules in the sample. And therefore, if you now obtain the absorption and fluorescence spectra for 2 orthogonal polarization directions, with one being parallel to the optical axis of the liquid crystal and the other being orthogonal, you will see very different spectra with absorption and fluorescence being much stronger in the case if the polarization direction is parallel to the liquid crystal director, along which all the dye molecules align parallel with their transition dipoles. So the other important feature is that such molecules of dye can uniformly distribute in the liquid crystal sample, and therefore there is the signal contrast that arises is mostly due to orientation of those dye molecules rather than due to the spatial concentration distributions. And because the absorption and fluorescence bands are again, just like in conventional applications of confocal microscopy, very separated with respect to each other, one can use detection and excitation at different wavelengths and perform confocal imaging. So in here you can see an application of this polarized fluorescence confocal microscopy to a liquid crystal cell, which is at the heart of many different technological applications of liquid crystals. So this is a nematic cell which at no applied electric field will have the liquid crystal director in plane of the liquid crystal cell, with all molecules pointing in on average the same direction prescribed by the rubbing of the two polyimide coated glass plates at the top and bottom. Now, if you look at the confocal microscopy image, and unlike with conventional imaging techniques, which we can obtain such an image in the vertical cross-section, as shown in here, you can see that the intensity of fluorescent signal obtained for parallel to the liquid crystal director is very strong throughout the entire vertical cross-section of the sample. However, if we apply the intensity of fluorescent light in those textures is presented using this relative intensity scale, the color scale shown in here. So the excitation laser powers are in here much smaller than milliwatt of laser power, and therefore they do not affect the sample. For example, they do not realign the liquid crystal molecules as you do this imaging. However, if you now apply an electric field to this liquid crystal cell, as depicted in here, the molecules of liquid crystal, the liquid crystal director, are realigned, and this is the so-called Friedrich's transition, as I mentioned it, the phenomenon of this electric field-induced realignment is at the heart of many different electro-optic applications and display applications of liquid crystals. However, you can notice from this cartoon representation that the strongest realignment is achieved in the bulk, in the central part of the liquid crystal cell. At the substrates, the molecules are kept by surface anchoring the anisotropic interaction of the liquid crystal molecules with this confining substrate. And therefore, the molecules at the substrate, there is a thin layer of liquid crystal in which molecules have not realigned. The director remains parallel to the substrate, even at relatively high electric fields. And so the realignment often can be achieved using electric fields of the order, the voltages of the order of 1 volt. And so the fluorescence confocal microscopy image depicted in here clearly visualizes this realignment in the vertical cross-section. So you can see that confocal microscopy allows us to obtain a side view of the liquid crystal sample and visualizes reorientation of liquid crystal molecules, because you can see a sharp decrease of intensity in the central plane of the liquid crystal sample shown in here. So to understand the principles behind this imaging, we can just simply use this cartoon that I showed on the right side of the slide. So whenever polarization of the excitation line is parallel to the transition dipole of the dye molecule in the liquid crystal sample following liquid crystal director, then there is a maximum, very strong intensity of fluorescence light coming from this particular volume, focal volume in the sample. However, if we have a mutually orthogonal orientation like shown in here, then there is essentially no or very little of fluorescent signal coming from the sample, because polarization is orthogonal to the transition dipole moment of both absorption and fluorescence. At the intermediate angles, one can obtain intermediate fluorescence intensity signals, and the relation between the intensity of emitted fluorescent light and the angle between the transition dipole moment and polarization of the excitation and detected fluorescence light can be described using this simple expression shown in here, showing us that the emitted fluorescent light is proportional to the cosine of the force power, to the force power of the angle between the liquid crystal director and the transition dipole moments of the diomolecules with respect to the polarization direction in the confocal imaging system. And so now not only we can use this approach for imaging of the spatial distributions of different components in the soft matter of biological systems, such as the ones shown in here, but also to visualize the patterns of molecular orientation. And the reason for this is that the fluorescent signal is strongly sensitive to the angle between the polarization direction and the transition dipoles of the dimolecule that follow liquid crystal director in the liquid crystal samples. Of course, from the point of view of imaging, there are many artifacts possible, because we realize that unlike in the case of biological applications or many other material science applications, we do have a liquid crystal medium which is a birefringent crystal. Therefore, it's much more difficult to focus, tightly focus light in such a medium. And this actually results in some resolution worsening, which can be roughly estimated using this expression shown in here. So the larger is the depth of scanning in the liquid crystal sample, the worse is the optical resolution, and the expression we show in here is such that the worsening is proportional to delta NZ, where Z is the depth of scanning, delta N is the birefringence of liquid crystal, which is the difference between the extraordinary and ordinary refractive indices of liquid crystal, and N average is the average refractive index of liquid crystal. So for materials such as 5Cb, you can easily estimate that at a delta N being 0.2, the depth of scanning of the order of 10 micron would give you some resolution worsening of the order of 1 micron. But because liquid crystal samples are usually relatively thin, and also many liquid crystal materials have relatively low birefringence, this technique is still very useful for study of those materials. Moreover, for many studies it's possible to use liquid crystals of relatively low birefringence, for example, materials which have delta N smaller than 0.05, and this mitigates this resolution worsening so that the much thicker samples can be imaged using this approach. However, the other artifacts can include possible depolarization and also light scattering in the liquid crystal medium due to thermal fluctuation of the liquid crystal director. On this slide, I would like to show you how powerful this technique can be in terms of visualizing molecular orientation patterns in liquid crystals. So this is a sample in which we have the cholesteric liquid crystal material in a batch geometry, so that different number of molecular cholesteric twists can fit into the thickness of the sample. And so the thin lines that you can see in here are the lines that you can see in conventional polarizing microscopy. it's very hard to tell much about them, except that there are thicker lines and thinner lines. However, if we would want to visualize the actual director structure behind those lines, it would be very challenging. Although this has been done before using just polarizing microscopy textures of this kind and some understanding of structural organization of liquid crystals. Now, in the case if we use fluorescence confocal polarizing microscopy, the nature of those lines, those defects, can be visualized very directly. And so the images that I've shown here correspond to different lines as one would go to the parts of the sample from thinner to the thicker part of the sample. And so you can see that the thinner lines shown in here and in here correspond to the edge dislocation in cholesteric layer structure, and they correspond to different, to the tau minus 2, lambda plus 2 disclination pairs depicted in here. However, in the thicker part of the sample, we can see that the lines, the defect lines are much thicker, and the vertical cross-section of the sample along in the section perpendicular to this line allows us to understand that we now have insertion of two different cholesteric layers, and the disclination pair that's observed is the lambda minus 1 over 2 lambda plus 1 over 2 disclination pair. So this is now a dislocation in this layered system of the Burgers vector equal to cholesteric pitch. And so, again, information of this kind would not be possible to visualize using just a two-dimensional image of polarizing microscopy depicted in here, but can be directly visualized using the fluorescence confocal polarizing microscopy, as this technique allows us to obtain a side view of the liquid crystal sample and a three-dimensional image of molecular orientation distribution in such samples. The examples I show here show even more complicated structures that can be achieved, in particular the terms of the dislocations in the cholesteric layer structure. And so, again, in conventional microscopy, one would only see a two-dimensional view of such a complicated structure, but in confocal microscopy we can obtain in-plane sections and also different vertical cross-sections depicted in here by those different lines in different directions, like for example B and B would be this one, C and C would be this one, and so on. And so by obtaining those different slices of the sample, you can easily get insights into the director structure and molecular alignment distribution in the two-dimensional sample. Moreover, this technique allows to even achieve quantitative comparison of the experimental results obtained using the microscopy with the theoretical predictions. So what you can see in here is an edge dislocation of Burgers vector equal pitch, and because of this dislocation, the layers above and below it depart from the flat orientation. The different theoretical models, nonlinear theory and linear theory, predict different layer displacements as a function of coordinates for this particular case. And so the theoretical predictions given by linear theory are plotted in here by dashed lines, whereas those given by nonlinear theory are plotted using solid lines. The dots correspond to the experimental data obtained by simply fitting using those layers above and below of this dislocation. And you can see that the nonlinear theory describes the results, the obtained result, much better than the linear theory. And so the reason for being able to do it, as we mentioned before, to do this visualization of patterns of molecular orientation is the sensitivity of the fluorescence intensity to the orientation of the dye molecules and the liquid crystal director with respect to polarization of the excitation line. So, as I mentioned before, this strongest signal corresponds to the situation of mutually parallel orientation, and the weakest signal to the orthogonal orientation. Because the fluorescent signal is a result of absorption and emission processes, both of which are proportional to the dot product of the director, liquid crystal director, and polarization orientation, and therefore the emitted fluorescent light is proportional to the cosine of the fourth power of the angle between the polarization direction and the liquid crystal director. So, however, this simple expression that I already showed before does not account for many different things. So, although it's very useful to understand how the fluorescence intensity depends on the angle between the liquid crystal director and the polarization direction in the confocal microscopy, one needs to understand that many other things also influence the obtained fluorescence intensity textures. And so, first of all, the imaging in this case, just like in the case of isotropic fluids, is diffraction limited, and as we know, as we discussed before, there is even additional worsening of resolution due to the birefringent properties of the liquid crystal medium. So, if one would like to model the fluorescence intensity patterns in confocal microscopy, those all effects can be taken into account, provided that we know the liquid crystal director orientation for a given structure, one can calculate the fluorescence intensity distribution in either in-plane or vertical cross-sections of the sample. So in here you can see that the fluorescence intensity textures can be calculated using this weighting function, which is given by can be given by Gaussian distribution. Of course, in the case of vertical cross-section, we understand that the resolution is worse in the axial direction than in the in-plane direction, and this can be taken into account too. So using those expressions, one can calculate what should be the fluorescence intensity distribution for a given director structure, and therefore those computer simulated results can be then compared to experimental results. So what is shown here is the images, computer simulated images for different polarization orientations obtained for the very same fluorescent, for the very same confocal domain in a symmetric liquid crystal. And so this image has been obtained for polarization in confocal microscope being vertical in this direction. The image in here was obtained for horizontal orientation, and this is a vertical cross-section of the same sample. Now, those computer simulated images can be compared to the respective experimental images obtained for the same orientations, vertical and horizontal orientations of the polarization direction. And based on images of this kind, both in plane and also vertical cross-sections, one can reconstruct complex patterns of molecular orientations or layered structures, like in the case of this particular Smalyukh liquid crystal shown in here. And so, because we can compare the expected FCPM images with experimental ones, we can assure that the structure that we deal with corresponds to a particular model that we have in mind, like that of the focal conic domain shown in here. Moreover, not only it's possible to use this technique for imaging of the thermotropic liquid crystals, such as the smectics and pneumatic liquid crystals we discussed before, but also the liquid crystal phases and structures and patterns formed by lytropic systems. And in particular, here you can see the liquid crystal sample formed by the DNA molecules forming this pattern, and in order to achieve labeling of the DNA molecules in this case, we used the dye molecules which intercalated between the base pairs of the DNA molecules, therefore being with their transition dipole moments orthogonal to the long axis of the double helix DNA shown in here. And therefore, when obtaining the polarization images shown in here for two mutually orthogonal polarization directions, we can visualize those patterns of molecular orientation, and not only in the plane of the sample, but also in the vertical cross-section of the sample. So you can see from those images that the intensity patterns are kind of complementary with respect to each other, and whatever corresponds to strong fluorescent signal in this case, so the intensity, the color intensity scale that we use in here is similar to the one I showed before, and you can see that the images are kind of complementary with respect to each other, which does make sense, telling us that we are able to visualize the patterns of molecular orientation using this technique in lytropic liquid crystals of DNA as well. Moreover, we can also utilize somewhat different approaches than what we just discussed. In particular, one can use other labels of the DNA molecules, such as yo-yo or popo dyes, and those dyes are known to very strongly bind to DNA molecules, so that then those small quantity of labeled, fluorescently labeled DNA molecules can be mixed with unlabeled DNA molecules. And then in fluorescence confocal microscopy, of course, we will be able to see only the dye molecules which have been labeled, as those shown in here. And then if we colocalize a regular polarizing microscopy image with the fluorescence image shown in here, we realize that the individual thin stripes on this texture correspond, fluorescence signals, have signals of fluorescence corresponding to individual single DNA molecules. And so therefore, using this approach, one can also visualize the complex orientation patterns in the liquid crystal sample of DNA. And so with this, I would like to conclude my lecture for today. So I hope I was able to demonstrate that confocal and multi-photon fluorescence techniques allow for three-dimensional imaging and imaging of concentration distributions and material composition in both biological and soft matter systems. And they can also allow visualization of orientational patterns and systems with long-range orientational ordering, such as liquid crystal media. Thank you for your attention.